And that's where we're at now. So we covered radio waves, we looked at microwaves, and we looked at infrared. And now we're at visible light. And if you notice, it's a really tiny sliver. It's actually the smallest sliver within the electromagnetic spectrum. And we use the mnemonic, I guess, Roy, red, orange, yellow, green, Roy G, Biv, indigo, violet, blue, indigo, violet. And so, and it's just a helpful way to be able to picture this, right? Um, Red has the longest wavelength, so just like radio and micro and infrared, it has longer wavelengths. Ultraviolet has the smallest wavelength out of all of them, and it also has the highest frequency. And so you can picture that. And so visible light we've got, and then right after visible light, right after violet is ultraviolet. And it's kind of interesting here what they did. You've got your prism, the light spreading out. What about this area right here? Just beyond violet. So someone got a photoreceptive object and placed it on that side, and it actually was exposed because of the ultraviolet light. And it has a smaller wavelength than visible light and a smaller wavelength than violet. In 1801, Ritter detected it by placing that plate there and said, okay, there's light beyond, the violet, what we can see. And the absorption of UV, does help our bodies provide vitamins from the skin, but if we have too much, an overdose is harmful. Fortunately, only about 5% of UV light passes through the ionosphere, the upper layer of the atmosphere, and so most of it is sent back out, reflected out. Next, we have X-rays, and these even have smaller wavelengths than UV. And as we go from left to right, we get higher frequency, higher energy. And so this scientist, and I would butcher the pronunciation of his name, in 1895 created rapid deceleration of electrons by sending electrons through a tube at high speed and crash into a metal. And as they crash into the metal, it slows down and emits X-rays. And so this is actually a picture of a person's hand with a wedding ring. And the way the X-ray works is that our bones actually absorb the X-rays, and then the X-rays that don't get absorbed pass straight through and then expose the film. And so, for instance, let's say you had a break in your finger. It would be like this. You'd have kind of a gap in here where the light would, the electromagnetic waves would pass through, and you'd be able to see the break in your hand. And so this is his wife's hand taken on 22nd December 1895. It's the first X-ray ever created there. All right, and then we get to our final one, gamma rays. Gamma rays are the most intense. They have the highest frequency, highest energy. They have the smallest wavelength. And the way that these are created are from nuclei of different atoms that typically this happens when it undergoes a radioactive decay, alpha decay or beta decay. And so they can be quite dangerous in large quantities, and they're created in the nuclear reactions. They're also created in neutron stars and pulsars. And you don't want too many gamma rays, being sent into your body. They're very destructive. They're discovered in 1900 by Villard, and that completes our electromagnetic spectrum. I found this was an inspection of a cargo container using gamma rays, and it's some of the things are being absorbed there, some of the rays, and so you can kind of get a picture of what's happening. So how we see humans, we can pick up visible light. Some animals, insects and birds can see UV. But it's unlikely, scientists think that animals can see infrared, but they can definitely sense infrared, and snakes can interpret infrared rays in their brains get a better understanding of their surroundings. You can see light here. Light's passing straight through. It goes through a lens, and then that focuses back onto our retina, which is in the back, that has rods and cones. We can, pick up the light there. So there's a mnemonic that can be helpful for us to memorize the electromagnetic spectrum. It's a little goofy, but I think it works pretty well. So each word represents the type of wave or type of electromagnetic wave, and we're going from longest wavelength with radio waves to the shortest wavelength with gamma. Radio waves have the smallest amount of frequency, smallest energy. Gamma has the highest frequency, highest energy, right? So you can remember this through this mnemonic. Real Martians invade. Roy G. Biv using X-ray guns. So radio waves real, Martians, microwaves, invade, infrared, Roy G. Biv's the color spectrum, using for ultraviolet, X-ray, and then guns for gamma. So how is light produced? Well, radio waves can be produced by moving charge back and forth, just like we saw in that antenna, currents going up, then back down, and then up, then down, and through that we're creating electromagnetic waves. The frequency of visible light cannot be produced by moving charge. We can't make it go up and down fast enough. So what has to happen is electrons go from higher energy levels around the nucleus to lower energy levels, and a photon of light is released in that case. And so the way that we can visualize that, if you want to draw it out, this represents the different levels around a nucleus. The energy levels surrounding the nucleus. And let's say that we had a photon in an excited, or an electron in an excited state. What will happen is if that electron is in a higher state and there's space down below, it's naturally going to drop down. And what will happen as it drops down, it's going to drop down and it's going to have a certain amount of energy. So whatever energy drop that it has is going to be the energy of that photon that's shot out. And the energy of that photon is going to be very, very specific. We're going to be able to calculate that here using this equation. The energy of the photon is equal to Planck's constant times the frequency. So visible light is from 750 nanometers of length, of wavelength, to 400 nanometers in terms of energy, 4 times 10 to the 14th to 7.5 times 10 to the 5th hertz, or 10 to the 14th hertz. And that's our frequency range for visible light. So with a light bulb, and we've talked about this before, the filament itself gets hot, and as it heats up, the electrons go to an excited state and go back down, and then release actual photons of light. And then once they're de-excited, they can get excited again, and then drop back down and shoot out photons. When we talk about sources of light, it's important to know what kind of light we have. Incoherent light is emission of light. It's uncoordinated and random, and pretty much almost all of the light sources that we have are incoherent. Now, coherent light and is where light is in the same direction and it's all in the same phase. And really, with coherent light, you're dealing with lasers. Here's a picture of some non-coherent photons of light here, where you've got random wavelengths, random frequencies. The wavelengths aren't lined up with each other. And then here's coherent light, where the wavelengths are matched up together, and they have the same wavelength. And this would be like laser light. And so if it's coherent, they have the same wavelengths and they're all in phase together. If they have a single color and same wavelength, we'll call that monochromatic. Mono, one, chromatic, you can think of a light or a color, one color.